Today's lecture is for semester 2, uh, paper 3, based on electricity and magnetism, and the topic which we will discuss today will be number 1, torque on a current loop. Number 2, ballistic galvanometer. I think it will be visible. I think will. Number 3, current and charge sensitivity. Number 4, electromagnetic damping. And number 5, finally we'll do logarithmic damping. So these are the topic which we will discuss today. First one will be, that is the torque on a current loop. So we'll just see how it could be derived. Here we are having here a squarish loop, or the rectangular loop rather. The length of the loop is L and the breadth is B. The magnetic field B, uniform magnetic field B, is acting on it. Now the force which will act on the wire will be given by I B into B. Here on this wire it will be ILB. Again on this wire it will be IB into B, and along this wire it will be again ILB. So what we will see, we will assign the name force F1, F2, F3 and F4, and we always assume over here that the current I is moving in an anti-clockwise direction in the loop, the rectangular loop. We'll see that the force F1 will cancel out F3, and similarly F4 will cancel out F2. So this topic basically is torque on a current loop. Now what we'll do is that we'll just tilt the loop. So in this particular case, basically if the forces, they are cancelling out each other, that is F1 is cancelling out F3 and F4 is cancelling out F2, so ultimately no force will be acting on the loop. The resultant will be 0. So what we will do next is that we'll just try to tilt the loop. Okay, so it will make again an angle theta. We are having this loop again, it will make so what we'll do is that we'll just tilting it. So now the loop is something like this. So it will be in a new position, which you can see over here, and it makes an angle theta. Yet it moves along this particular line. So what you can see over here is that now this has been shifted to new position over here, right, the dotted line rather, which you can see in the figure. Now it makes an angle theta with it. Now again the current is same. What we have earlier assumed, it's I. The magnetic field B, it's coming out from the, it's pointing towards me. So what you can see is like it's very, very clear now. Now the force again over here will be F1 along this direction, or what is it's F3 rather, F3. Earlier what we have seen is F3, it's going to be F1 along this direction, F4 along, or rather F2 along this direction, and F4 along this direction. So now what will happen is that again F2 will cancel out F4. Okay, but the thing is that what will happen to this F3 and F4? Now what we can see over here is that there is an angle theta, and this is a perpendicular distance which we can see over here. So this distance, the length is B, so this will be B by 2, and this is theta, so this particular line will be B by 2 sine theta. Okay, so the torque of F3 about, this be O, okay, about O has magnitude, let it be OPQ. So OP cross this is F3, so force into perpendicular distance, that is B by 2 F3 sine theta, and we know what is F3 is ILB sine theta. So F12 will have the same magnitude. Similarly, the torque of F1 about O will have the value again B by 2 I L B sine theta. Okay, so the total torque acting on the loop is therefore tau is equal to B by 2 ILB sine theta plus B by 2 ILB sine theta, which is equal to IAB sine theta, where A is equal to L into B, the area of the loop, the normal area. Now if vector A vector A is the area vector, of the loop. Okay, pointing in an outward direction. Okay, then tau is equal to I A cross B, okay, or tau equal to, put a vector sign over there, tau is equal to mu cross B, where mu is equal to I vector A is called the magnetic dipole moment. So this is one of the derivation as far as torque on a current loop is concerned. If it has n number of turns, then tau will be equal to NIA cross B, right? So this is how it works. Thank you.